In this video, I'm going to test the null hypothesis that four groups have equal means, and the study is relevant to font size on a mobile phone and the amount of time it takes to read material on that mobile phone, measured in, I believe, seconds. And so we have four different groups that read each a font size, and the lowest font size was 4, then 6, 8, and 14. So we got four groups. That should automatically discount the possibility of doing the protected Fisher's LSD. That's only appropriate for three groups. We have four groups. The next question to ask is, was the homogeneity of variance assumption satisfied? And let's just check and see if that was the case. Put time in there, font size in here, and options. Let's just look at the homogeneity test. And what we find is that we have violated the homogeneity of variance assumption. That's eliminating options right there. We can't do Tukey-Kramer's HSD. Now let's also look at sample size. Is sample size equal? I should have asked for that in the ANOVA. Let's see. Options, descriptives, and sample sizes are also unequal. So I've got four groups. I've got heterogeneity of variance, and I've got unequal sample sizes. I'm left with a small number of options here. Let's look at the skewness level, because that's going to impact whether I'm going to do a bootstrap analysis or not. So let's compare groups font size, and let's look at the skewness levels. Skew and kurtosis, and let's check that out. And what we find is skew is 0.8, not very bad, 0.11, and negative 0.23, not bad at all. Kurtosis, 0.35, 1.3, negative 1.15, and negative 1.05. These are all much lower than absolute values of 2 and 9. And even though there are some numerical differences between the skewness levels, it's not that bad. It's really not that bad at all. So in this case here, I would be confident with a parametric analysis that isn't based on bootstrapping, but I've got heterogeneity of variance and unequal sample sizes. I could do the Welch's F-test or the Brown-Forsyth, but I would then be stuck with having to do follow-up post-hoc tests. And the only one that's really, I think, is especially good, or the one that I taught in a textbook anyway, is the Games-Howell procedure. And the Games-Howell procedure is a single-step procedure, so I don't need to do the Welch's F-test or the Brown-Forsyth if I'm just going to use the Games-Howell procedure, which I could do. So let's actually do that to test the differences between all these means, 20.94 seconds versus 8.25 seconds, 9.37, and 12 seconds. So let's go into post-hoc, and we have Games-Howell. And we will find, we'll find again that I forgot to unsplit the data file. This is really just my sort of thing. And let's see what we get. Here are the Games-Howell multiple comparisons. What I'd also like is a chart of the means, but I'll show that in a minute. We can see that it took more time for people to read on average the font size of 4 than all other font sizes, 6, 8, and 14. All of these differences are statistically significant based on the p-values being less than 0.05. and also the upper and lower confidence intervals, which are not bootstrapped in this case. These are just asymptotic normal distribution theory confidence intervals based on the same procedure estimated here. 4 is slower. It's too small a font. People are taking too long to read a font size of 4. Now, when it comes to font size of 6, it looks like 6 is associated with the lowest numerical mean at 8.25, but it is not statistically significantly different from 8. Because 8 is negative 1.12 and the confidence intervals are intersecting 0. So I can't say that 6 is statistically significantly better than 8 with respect to the amount of time it takes people to read the material on the mobile phone. But we can find that 6 does take less time than 14, because that's negative 3.85. And we can see the means here, 8.25 versus 12.1. It's statistically significantly lower, this 8.25 versus 12.1. So this is a very long way to present results in terms of statistically significant differences. It's perfectly legitimate to do so, especially if we wanted to know the specific comparisons between the groups, and many people might want to know that. So this is a perfectly plausible way to analyze the data. we would conclude that 6 is statistically significantly faster than font size of 4 and a font size of 14, but we can't tell the difference between 6 and 8. Not statistically anyway. Numerically, we might push. Let's actually look at the graph. So here is the graph, the plot of the means, and we can see that 6 wasn't found to be statistically significant different from 8, but it was different from 14, and it was different from a font size of 4. And that could be a conclusion. Now, you could also consider doing a contrast analysis on these data to say that there is one bend in the means. I'm not saying that you would or should do that, but hypothetically, if you didn't get any significant results in this, or there was maybe just one that was statistically significant, you might consider doing a contrast analysis to try to push for the argument that there is a U-shaped function associated with the means. So let's actually do that. Compare means, one-way ANOVA, contrasts. Now, we can do it with the coefficients, which I'll do in a minute, but let's just do it with the quadratic function, which is the quick and lazy way to do it. And we get the quadratic function, the unweighted term, might as well focus on that one in this case, is 207.377 with 1 and 112 degrees of freedom, and it's statistically significant. So the quadratic effect, representing one bend in the means, and in this case it's a U-shaped function, is statistically significant. What we don't have is the test that doesn't assume homogeneity of variance. And we actually want to have that. So in order to get that, because the homogeneity of variance assumption was violated, we actually need to specify the coefficients ourselves. So let's see if I can remember them. So we want to go into contrast, and we have a U-shaped function. So let's deselect that. We have a U-shaped function. So we want to do 2, -1, -1, and 2 to reflect a U-shaped function. So it starts high, goes down low, and then comes back up again. So let's see what we get there with the homogeneity of variance not assumed test. And we can see that the t-value is equal to 25.30 with 54 degrees of freedom in the denominator. So it's really 1 degree of freedom in the numerator and 54 in the denominator. And that is a p less than 0.05. In fact, it's p less than 0.001. So the do not assume equal variances does support the alternative hypothesis of one bend in the means. And I probably wouldn't opt with that option here. I probably do want to know, is 6 statistically significantly better than 8? And in this case, I can't say it is. But I can say that 6 is better than 14 and 6 is better than 4. And 8 is also better than 4 and 8 is better than 14. So these results overall are telling us that a font size of 6 or 8 might be the optimal point with respect to speed. If we had a larger sample size, who knows, maybe we'd find 6 to be statistically significantly greater than 8 font size, but we don't know. We'd have to collect more data. It's just as likely to become less significant as more significant, so who knows what will happen. So that's how you could analyze these data based on the information I provided in the textbook. A little bit complicated because of unequal variances and unequal sample sizes, but that's happened so often in reality that you really need to know about these analyses.